In this video, we're going to talk about the basics of gradient descent. Gradient descent is an algorithm that is used to train all kinds of machine learning models. For example, neural networks and logistic regression. After this video, you will understand this picture of the height map and the landscape and how that relates to the algorithm gradient descent. First, we describe three types of training procedures. Some models don't need any training at all. These methods use instance-based learning. The k-nearest neighbor classifier is an example of such an approach. This classifier doesn't have a clear training phase. All computations are done when this model is making a prediction. It then finds the neighbors and does a majority vote. Because it compares the new object to the training instances, this is called instance-based classification. No computation or training is necessary before making predictions. Then there are some machine learning algorithms that train by using a formula. This is called closed-form training. Linear regression is a procedure that can be solved using closed-form training. The third option is iterative training. This means training is done in a loop. It is going to take several computations to train the model. During iterative training, usually something is optimized over time. This is called the objective function. Gradient descent is an example of iterative training. If you want to do iterative training, you need three ingredients. You need a model class, a cost function, and a way to minimize that cost function. Note that another word for cost function is objective function. Let's have a look at an example. We will start with linear regression. We need three ingredients for iterative training. Let's start with the model class. The model class for linear regression is given by all linear models. We can write all linear models as W transpose X plus a bias term W0. Each choice for W and W0 will give a different linear model. Now we need a cost function to choose among this very large set of models. For linear regression, the cost function is the mean squared error on the training set. This was the equation for the mean squared error. We indicate the objective function by the letter J, which is a function of W and W0. So each linear model is determined by some W and W0, and therefore each linear model has an associated cost, which is given by the mean squared error. Note that from now on I will drop W0. Please assume it is included in the vector W. The third thing we need is some way to find a linear model with a small mean squared error. With other words, somehow we need to find a W that minimizes the objective function J. How to find this W? Take a moment to think about it, pause the video, and then let's discuss the answer. Welcome back. There are usually two options that may come to your mind. The first is to try all possible linear models. The problem is there are infinite linear models. Maybe we can discretize the problem and try all of them and still find a good solution. The problem is that this is usually too time-consuming. If we're going to high-dimensional problems with more features, this approach doesn't work anymore. The computation will often take too much time. A second option is to randomly pick a linear model and make small adjustments to it to reduce its objective value. This is the approach often taken with iterative training. I have prepared several widgets for you that accompany this video. Here you can try your hand at the concept of iterative training. Please solve the exercises in the widget and then we will continue with part 2 of this video.